if we are looking to find the area of the region between the curve, what's the first thing we need to do with this function? No, you're both wrong. Not just take an integral. If we're looking for the area of the region between the curve and the x-axis, what's the first thing we have to do? Because an integral doesn't just give us the area between the curve and the x-axis, right?
No, it's what you want to be called.
Okay, we could do absolute value, but we can, yeah, we can do absolute value, or we can just take a look and see what this graph looks like first. So 4 minus x squared looks like this, right? It's got a y-intercept of 4, and it's got, you know, it's downward facing parabola. What are the x-intercepts of it? Yeah, this is 2 and this is negative 2. So we could do an absolute value, or what we can do is we can just split it up into 2 different integrals. So if we're going to look at the integral from 0 to 2, that'll give us the area of that section that's above it from 0 to 2. And then we'll also have to do this section from 2 to 3 on its own. Everybody good with that? I'd rather split into 2 integrals and have to take an absolute value and then rewrite it as like a square root of the thing squared, because that's a little bit of a pain of an integral. So if we're going to integrate this, we're going to do 0 to 2 of 4 minus x squared dx. And then we need to add to it the opposite of this. So we're going to subtract the integral from 2 to 3 of 4 minus x squared dx. Okay? Because the section below the x-axis is going to be negative. Make sense or no? Everybody good there? All right. So we got 4x minus x cubed over 3 from 0 to 2. That's our integral, right? Minus 4x minus x cubed over 3 from 2 to 3. And so that becomes 8 minus 8 thirds minus 0 minus, and then this one is 12 minus, what is that? 27 thirds, which is 9. So 12 minus 9 minus 8 minus 8 thirds. And what does that come out to be? Hopefully my arithmetic is right there. 29 thirds. Or, did I say 29? No, that's not right. 30. 23 thirds. Yeah, 23 thirds.
Right?
Is that what you guys get if you do that arithmetic?
You're such a Jeff. Oh my god. I know.
Everybody good or no?
Sandra, do you already win? Oh, absolutely do it. I'm an 8 and it changed my life. Yeah, I thought I was a 2 for the longest time, but it never felt quite right. And then
Everybody good or no? All right, just making sure. Nobody was responding, so. All right, what about this one? How are we gonna do this one? This one's no longer area, so we don't care if it crosses through the x-axis. So what are we gonna do to integrate this? All right, one option is a u sub. Okay, if you're going to do a u sub, what are you gonna sub out? Okay, so if u is equal to r plus 1, then du should be equal to just dr. Yeah. Everybody agree with that? And this should then become what integral? Should become an integral of u squared du. But what has to happen with our limits of integration? They need to change, right? So if u is equal to r plus 1, well, this was an r value. -1 plus 1 is 0, so our new lower limit is 0. And 1 plus 1 is 2. Our new upper limit is 2. So now it becomes an integral from 0 to 2 of u squared, or u cubed over 3. Do we need to turn that back into r plus 1? Nope. And we'll just plug in our new limits. So this becomes 8/3 minus 0. What's the other option we could have done for this particular problem here? Did we need to do a u sub? We didn't need to do the u sub, right? We could have just expanded it out. So we could have had this as an integral from -1 to 1 of r squared plus 2r plus 1 dr. This would work just fine also. Yeah, r cubed over 3 plus r squared plus r from -1 to 1. So we've got 1/3 plus 1 plus 1 minus -1/3 plus 1 minus 1. Comes out to be 8/3 either way. Everybody good with that? So either way is fine. You can always simplify it down first, or you can use the u sub if you need to. About as simple of a u sub as we could possibly do, right? Because our du just is the same as our dr, but usually that's not the case. And so we're going to do a bunch of u substitutions later today. I don't know, they're somewhere along the way in what we're doing today. All right, we'll do a couple of these initial value type problems. And then I think we're going to do the u subs after that. So we want to find a function h of x with h of 2 equal to 3. So we're given an initial value or initial condition to this. That's why we call these an initial value problem. And we're given an indefinite integral, the indefinite integral of 3x squared plus 5 dx. So the integral of 3x squared plus 5 should be what? It should be x cubed plus 5x plus a constant. And so that's what h of x is equal to. And what do we need to do? We need to find the constant. How do we find the constant? H of 2, which is 3, should be 2 cubed plus 5 times 2 plus that constant. So we just plug in the initial condition that we're given, and these are like our basic differential equations, and solve for our constant. So what is our constant equal? -15. So our h of x function is x cubed plus 5x minus 15. Easy enough? Everybody good with that?
You're planning it. Yay! Nice.
All right. Why don't you guys do this one on your own? It should take you about, I don't know, 30 seconds. So ready, go. Everybody good with that?
Okay.
Yeah. All right. So
Well, so when you do like off-track, on-track, do you think you're gonna be limit by the end?
our integral here of cosine should have just been sine x plus a constant, right?
No, it's more like a.
And we know that f of pi over 2 is equal to 3, which is sine of pi over 2 plus our constant. Sine of pi over 2 is 1, so we got 3 equals 1 plus our constant, or our constant is what? 2. So f of x is sine of x plus 2, and f of pi ought to be the sine of pi plus 2. And what's the sine of pi? Sine of pi is 0. So we got 2. Is that y'all got?
So maybe in the future, you know, one, try to market here.
Yeah.
So like, instead of it being.
All right. Moving forward. Now we're going to get into our u subs.
Sorry, I did this a lot.
So we've got sine of x times e to the cosine x. So we're going to need to make a substitution because this is not just a easy integral with a formula that we can just follow. So what do we need to substitute out?
No, I mean, I think they're good for this quarter. I think.
So generally when we're looking for what to substitute out, it's going to be whatever piece of it makes it complicated that we can easily take the derivative of. So the piece of this that makes this complicated is the e to the cosine x part, and the cosine x part of that is the specific piece of it that makes it difficult to deal with, right? Because e to the u we could just integrate as e to the u. So if we get rid of the cosine and make u equal to cosine x, then we're going to end up with hopefully just something like a constant in front of our e to the u. So if u is cosine, then what is du? Du ought to be negative sine x dx. And so if we look into our original integral, we can see that we don't have negative sine x dx, but we do have the sine x dx. So we've got a piece of what we need to have in there, right? We got the sine x dx. So we just need to build our du in there so that we can replace everything else, the negative sine x dx, with the du. So we're going to rewrite this as an integral of negative sine x times e to the cosine x dx. But I can't just throw a negative in without putting another negative sign. So we'll put a negative inside and a negative outside. And this now becomes the opposite of the integral. And negative sine x dx is our du, and cosine x is our u, so it just becomes e to the u du. And from there, if you want, you can put the negative inside and integrate, or you can leave the negative outside. It doesn't really matter. This integral is negative e to the u plus our constant, and u is cosine x, so we'll resubstitute in negative e to the cosine x plus our constant. And the point often comes up about, well, what about that negative being outside the integral? Shouldn't it be the opposite of the integral of e to the cosine x plus c? Like this, right? Because technically that negative sign's outside, but also we could bring the negative inside, and we could have negative e to the cosine x plus c, which is what I wrote. Well, those are effectively the same thing, because if I distribute the negative through, I still have negative e to the cosine x, and minus a constant, the same as plus a constant. The only time that matters is when you're actually solving for the constant. And so since we're not doing that right now, plus a constant and minus a constant are the exact same thing. So the only time we have to be careful about that is when we are actually evaluating and trying to find that constant. And either way you do it is perfectly fine. It doesn't really matter. But we'll talk more about that when we do our differential equations. Everybody good? Any issues with that? Everybody remembers how to do U substitutions? That should be review for everybody. All right. What about this one? X squared times the square root of 5 plus 2x cubed. Not just a simple rule that we can follow for this one, so we're going to have to do a U sub. And the more complicated piece of this is the square root of 5 plus 2x cubed, right? So we're going to try to substitute out all of the inside of that square root, because the square root of u is something that we could easily integrate. So we're going to let u equal 5 plus 2x cubed, which makes du equal to what, 6x squared. And we don't have a 6x squared, sorry, 6x squared dx. We don't have a 6x squared in there, but we can build the 6x squared dx into there by throwing a 6 into it. If we put a 6 on the inside, then what do we need to do with the outside of the integral? Put a 1/6 outside. So 1/6 the integral of 6x squared, and then our root 5 plus 2x cubed becomes root u, right? And the 6x squared dx will become our du. So we got 1/6 the integral of root u du, and then we just integrate that. And so what's the integral of u to the 1/2? Should be 2/3 u to the 3/2 plus our constant. And what does that give us? 1/9, and then u was 5 plus 2x cubed to the 3/2 plus our constant. Officially, that 1/6 gets distributed through that c, but it's really, 1/6 of a constant is still a constant. If you just write c, that's fine with me. Because note, we could also have just brought the 1/6 in when we integrated, and then it's the same. So everybody good there or no?
It really depends on how you work. So like I know Jeff, I'm the person who has to like do one whole step. Whereas I'm the kind of person who can work on them all the time.
All right, what about this one? All right, if we just let u equal 7x, Darius, we're gonna have a little bit of a problem. Because you know how to just straight up integrate your cotangent, unless you memorize the rule from what we proved last year, maybe. But
yeah,
what I'm going to do is I'm going to rewrite this as the integral of cosine of 7x over sine of 7x dx. And then I'm going to substitute out the u equals sine of 7x. So if u is equal to sine of 7x, then what does du equal to? 7 cosine 7x, and we don't quite have that, but we almost have that. So we'll just build it in with a 7 and a 1/7.
yeah.
And so now this becomes 1/7 of the integral of du, 7 cosine 7x, forgot the dx, 7 cosine 7x dx over u, which gives us 1/7 the natural log of the absolute value of u plus our constant. And we'll just replace the u. So we got 1/7 natural log absolute value of the sine of 7x plus our constant. Everybody good with that or no? Any issues there? Everybody good?
Stop it. If you need to get your fix, utilize your free webinar stuff, and you will rapidly find that it's not worth your time. So, this tutorial is also not worth it.
Okay. All right, we might want to remember if we want to integrate cotangent, just cotangent x, right? Dx. Or if we just want to integrate tangent x dx, we can come up with some formulas to do those. So let's do that real quick. So this one is the integral of cosine x over sine x dx, and this one is the integral of sine x over cosine x dx.
I know that course is not cheap.
And here we'll do the substitution for u is equal to sine, so du is cosine. So we end up with du over u for natural log absolute value of u, or natural log absolute value of sine x plus your constant. So maybe memorize that one for cotangent. And then this one, we're going to do the substitution for cosine. And if u is equal to cosine x, then du is equal to negative sine x dx. So we'll put in the negatives. Negative integral of du over u gives us negative natural log absolute value of cosine x plus your constant or tangent. So I'd suggest memorizing those two just to make your life easier, but also know how the u substitution works for them, just in case you're asked to do that at some point. Everybody good there? No issues with that? Everybody good with that? You're all going to memorize those? Perfect. Even though no one's responding. All right, what are we going to do with this one? I don't think I can rewrite that as tangent squared, but I could rewrite it as secant squared. Yeah, Nick, to answer your question, yes. You can also write the integral of tangent x as natural log of secant x. When we finish this problem, and I'll go back and show you guys why that's true in a second. But this one becomes secant squared 2x dx. So our u substitution is just going to be u is equal to 2x on this one, because the integral of secant squared u we should know to be tangent of u, right? So if u is 2x, then du is 2 dx. So we'll put in a 2, we'll put in a 1/2. We end up with 1/2 of the integral of secant squared u du, or 1/2 of tangent of u plus our constant, or 1/2 tangent 2x plus our constant. And so these simple u substitutions like this one, you're going to want to get really used to those and be able to do those in your head without having to write it out. because in a day or two, we're going to start doing some much more complicated integrals that require you to do a lot of these u substitutions within the same integrals, or at least a couple of them. And if you're writing it out every time, it's going to just make your life a lot more complicated. So make sure you memorize how to do these simple ones in your head. And then Nick, to answer your question, yeah, negative natural log, right? This is just a -1 that's out in front of there. So this -1 can be applied in here as an exponent on the cosine x. So if we wanted to, we could say that this is the natural log of the absolute value of cosine of x to the -1 power, not the inverse cosine, right? But just cosine of x to the -1, which means 1 over cosine x, or natural log absolute value secant x. So yeah, either one of those is fine. Everybody good with that and this? And on the integral of tangent 1, negative natural log absolute value cosine or natural log absolute value secant, neither of them is better or worse than the other. They're both fine. So whichever one you feel like using or seems like it's better in the problem, go for it. All right. What about this one? What are we going to do here? Gonna have to rewrite some trig, I think.
Oh, I love it. Yep.
Anybody have an idea on that? What are we gonna do here?
Oh, okay.
No, but yeah. Yeah, there we go. So Nick, you got that there. Cotangent squared, right, is equal to cosecant squared minus 1. And because 1 plus cotangent squared is equal to cosecant squared. So cotangent squared is equal to cosecant squared minus 1. So this becomes an integral of cosecant squared 3x minus 1 dx. And first off, we can just do this minus 1 piece, right? That's just minus x plus our constant. And then how are we going to do the cosecant squared 3x piece? You're going to use a u sub, right? So if u is equal to 3x, then du is 3 dx. So we'll put in our 3, we'll put in our 1/3, and we end up with 1/3 the integral of cosecant squared u du minus x plus our constant. And what's the integral of cosecant squared?
Yeah, so.
Should be negative cotangent. And technically we get a second constant in there, but a constant plus another constant is just a constant. So we'll just keep one constant there. We got negative 1/3 cotangent of 3x minus x plus a constant. Any issues with that? Or everybody good with that? Makes sense. So make sure that you don't forget you can rearrange your trig functions into something that's easily integrable. Any questions or problems there? All right, why don't you guys try and do this one on your own, see if you can come up with a way to do this one. I'll give you guys like 2 minutes. Ready, go. All right, so what do we do here?
It also takes me longer to figure shit out.
What'd you guys do? First, probably you split it up into what? Yeah, cosine times the cosine squared x. And then with any luck, split the now changed into cosine x times 1 minus sine squared x dx. And then you should have made a u substitution with u equal to sine x with du equal to cosine x dx. So we've got the cosine x dx, and that allows us to get rid of all of the trig functions completely and just turn this into an integral of 1 minus u squared du. Everybody good with that? All right. And so we end up with u minus u cubed over 3 plus our constant, or what was u? U was sine x. So sine x minus sine. Oops, I don't know why I wrote that. Sine cubed x over 3 plus our constant. Any issues there? Everybody good?
Yeah, exactly.
We separated the cosine x and the sine 2x cosine x. I see. You did cosine x minus cosine x sine squared x. Yeah, that's fine. I mean, yeah, if you want to do that, that's fine. There's no particular reason to, I don't think, but it's fine. You get the same answer exactly, or probably not? Yeah, it probably should have been exactly the same. Yeah, should have been the same. Yeah, that's fine. Doesn't matter. All right, next one. And then this one's a definite integral, so we're going to make sure that we evaluate properly at the end here. So what's the substitution that we're going to want to make? Is one piece of this the derivative of another piece of it? If one piece is the derivative of the rest of it, then we'll make the rest of it our u. So since the derivative of tangent is secant squared, we let u equal tangent x du ought to be secant squared x dx. So we should be able to rewrite this as an integral of u du. And our 0 and our pi over 3 need to be reevaluated as a u value. So what's the tangent of 0? It should be 0. And the tangent of pi over 3, you should know what that is. What is the tangent of pi over 3? Should be root 3. Yep. And so we end up with u squared over 2. No constant this time because it's a definite integral, 0 to root 3. Plug in root 3. Root 3 squared is 3. So 3 halves minus 0, or just 3 halves. Everybody good with that? Any issues with that? All right. Last one for today. Integral from 0 to 1 of x over x squared minus 4. So what's the substitution we're going to make here? the denominator piece of it, the x squared minus 4, because its derivative looks similar to x. And we need to clear out all that junk in the denominator there so that we can just have it as one single variable and can integrate it using natural logs. So we'll let u equal x squared minus 4. And du will be 2x dx. So we're going to throw a 2 here and a 1/2 on the outside. Everybody good with that?
So good.
We got 1/2 of an integral of du over u. And our limits of integration need to change. 0 squared minus 4 ought to be -4, and 1 squared minus 4 ought to be -3. And so now we end up with 1/2 the natural log of the absolute value of u. And we'll evaluate that from -4 to -3. Everybody good or no? Okay, so natural log of absolute value of -3 is just natural log of 3. And minus natural log absolute value of -4 is just natural log of 4. So we've got 1/2 of the natural log of 3 minus the natural log of 4. That answer is good. Personally, I'd rather rewrite it as something like 1/2 natural log of 3/4. That would be good also. If you want to bring this 1/2 in as a square root, that's fine too. Natural log of √3/2, that's also good. Really, any of these 3 answers would be acceptable. Everybody good with that? That's basically it for today. A couple things to remember. One, trig functions can be rearranged and rewritten, so do that if they help, if that helps. And when you do a u substitution, make sure you can build your du and make sure you change your limits of integration if you have a definite integral. Any questions on anything today? All right, so I will post up some practice integrals. Some of them will just be regular integrals. It'll be really easy. Some of them will require u substitution, all that fun stuff for you guys to work on tonight. We're going to talk about some of the basic rules for integrals tomorrow, like, that you can, we'll talk about tomorrow. We're going to talk about some of the rules for integrals tomorrow, and then the rest of the day tomorrow, we're probably going to move into talking about integration by parts, which is a completely new topic. So I'm going to actually post up a couple different things tonight. One of them is going to be a few practice mean value theorem problems, and the other one will be just a bunch of practice integrals. So look for both of those tonight. I'll make the mean value theorem one that, remember we did the mean value theorem the other day. I'll make that one due tonight and the other one due tomorrow, because the integral one, which is a bunch of integrals, is going to be a little bit longer, a little more time consuming. So